Welcome back. We'll now continue with our discussion on the Laurent series. Okay, so we'll start with the Taylor series. Okay, so we have seen from the Taylor series expansion that if I have a function f of z which is analytic everywhere on a closed contour C, okay, then it can be expanded about it as a Taylor series about any point z0 inside C, and this Taylor series expansion is this, that is f of z0 is summation a n z minus z0 to the power n, and these coefficients a n's are given in terms of the nth derivative of the function and the value that it takes at z equal to z0. And from the generalized Cauchy integral formula, we can write this also as 1 by twice pi I integral of fz divided by z minus z0 to the power n plus 1. So this is basically your Taylor series, and if you note here the Taylor series, n equal to n starts from 0 and goes all the way to infinity. Okay, so that means these are all positive quantities. Okay, so in the Taylor series we only have positive powers of z minus z0. In Laurent series what happens is we'll get negative powers also. Okay, so how does that happen? It happens because you see we are assuming that the function is analytic everywhere and on the closed contour. Okay, but if suppose inside this closed contour C, if there exists at least one singularity, okay, so at least there is, let's say, only one singularity, and say that that singularity is at z0, then we can no longer represent this function as a Taylor series, because the Taylor's theorem, it says that this is possible only if the function is analytic, and the moment we have one singularity within C, then the function is no longer analytic, then we can no longer represent this as a Taylor series. So in that case we have to represent this as a Laurent series about z equal to z0, and this Laurent series will involve the negative powers of z minus z0 as well. So what will happen is, instead of n going from 0 to infinity, it will be from minus infinity plus infinity. So this n can take negative values as well. Okay, and the coefficients, this a n coefficients, the expression remains exactly the same. Okay, the same expression as this. Okay, so of course we'll be, in case of Laurent series, we'll be using this definition of the coefficient, because the negative derivative is not defined. Okay, all right, so suppose at z equal to z0, the function f of z, it has got a pole of order p. So we'll take the case of a pole, okay, and see how it leads us to the Laurent series. So suppose at z equal to z0 we have the function f of z, it has got a pole, and the pole is of order p, but it is analytic everywhere else except at this point z0, where there is a pole of order p. It is analytic everywhere on the interior and on the circle C. Okay, so now what we do is, using this function we will construct another function. Okay, using the function f of z, we'll construct another function g of z. So g of z we define as z minus z0 to the power p f of z. Now this function will be analytic at z0. You can just go to our discussion on poles. Okay, the definition, from the definition of poles. Okay, so if this function f of z is not analytic because it has got a pole of order p at z equal to z0, then z minus z0 to the power p times that function will definitely be analytic. Okay, this is the basically definition of the pole. So this function will be analytic everywhere. Okay, so that means this function g of z can be expanded as a Taylor series. So remember, Taylor theorem, it says that only an analytic function can be expanded as a Taylor series. F of z is not analytic because it has got a singularity. Now this singularity, we are assuming that singularity to be a pole of order p. Okay, which we can of course generalize this to an essential singularity later on. So it's a pole of order p, so that's the singularity. So we can always construct another function which is not going to, which will not have a pole of the same order. How do you get that? Just multiply z minus z0 to the power p to that same function. Now this g of z is going to be analytic, and the moment this g of z is analytic, that means from Taylor's theorem this g of z will now have a Taylor series expansion. So by Taylor's theorem, g of z can now be expanded as a Taylor series about z equal to z0. So let's say it is this, g of z is equal to summation n equal to 0 to infinity b n z minus z0 to the power n. Okay, this is what we have. Okay, so now what is g of z? G of z is z minus z0 to the power p f of z. Okay, and this one we just write down the first few terms. N equal to 0, we have b0, n equal to 1, b1 z minus z0, and so on, bn z minus z0 to the power n. Okay, now this z minus z naught to the power p, you just bring it over to the right hand side. So here we will get b naught by z minus z naught to the power p plus b1. Okay, so we have already a z minus z naught. When you divide by z minus z naught to the power p, we'll get z minus z naught to the power p minus 1, and so on. And so when you this is divided by z minus z naught, we'll get z minus z power n minus p. Okay, so call this as equation number 1. So what we do is this b naught, we just rewrite it, we give it another name, we just call it as a minus p. This b1 we'll call it as a minus p plus 1, and so on. And this bn we'll just call it as and so on. Okay, and we will find, see, this f of z, we are able to write this as a series. Of course this is not a Taylor series because it has got negative powers of z minus z naught, but it's nevertheless it's a series. Okay, the first element is a minus p divided by z minus z naught to the power p, and so on. And there is going to be a minus 1 term divided by z minus z naught. By the way, this a minus 1, we will see that in the next lecture. This is known as a residue. It's an extremely important quantity. Okay, we'll more about that little later. In the next lecture, we'll discuss this in great detail. Okay, so this f of z is basically a series which looks like this. Let's call this as equation number 2. Now if you compare the coefficients in equations 1 and 2, compare the coefficients in equations 1 and 2. Okay, so when here the coefficient, this b0, here the coefficient will be a minus p. Here when the coefficient is 1, here it will be minus p plus 1. So if you compare this, we can see that a n is equal to b n plus p, right? A n is equal to b n plus p. Okay, so if I put n equal to minus p, okay, if I put n equal to minus p, so minus p plus p, this is going to give us b0. A minus p is the same as b0, and you can work it out. This, it holds good for all the other coefficients. So a n is equal to b n plus p. So the coefficients from the Taylor's theorem, okay, these coefficients that we have here, okay, these coefficients that we have here, using the Taylor's theorem, these coefficients are given as bn equal to 1 by n factorial g, the n derivative of g at z naught, and which is equal to 1 by twice pi I, the closed loop integral of g of z by z minus z naught to the power n plus 1. Okay, this is from the Taylor's theorem. Then what we do is we use this relationship between a n's and the a coefficient and a b coefficient. We use this in equation number 4, and we find that a n will be simply equal to 1 by twice pi I, the closed loop integral of gz divided by z minus z naught to the power n plus p plus 1. So all you have to do is this a n is equal to b n plus p. Okay, so so this n we replace with n plus p, so that will give us a n, and here also you replace n with n plus p, that will give us n plus p plus 1. So this is what we will get. Okay, so next step is very easy. All you have to do is just this g of z we replace with z minus z naught to the power p f of z, just replace it that. So now this will get cancelled and this p will get cancelled, and as a result a n is equal to 1 by twice pi I, closed loop integral of f of z by f of z dz by z minus z naught to the power n plus 1. So expression is exactly the same as in the case of a Taylor series. Okay, so here n equal to minus p plus 1 minus 2 and so on. And what is p? P is the basically the order of the pole. Okay, p is the order of the pole for f of z at z equal to z naught. So that's basically the Laurent series. Okay, so if a complex function f of z has a pole of order p at z equals z naught, we can expand this as a Laurent series, and this is a Laurent series, and the difference is instead of n starting from 0, n will now start at minus p and go all the way till infinity, and these a n's are given by this formula. Okay, so now what we can do is we can divide, we can break this down, right? Because we have here a n goes from minus p to infinity, so we can always break down this one, because the negative powers, wherever we have negative powers, that you take it as one series, and the positive powers you take it as another series. You can always break this down as two parts. Okay, so this will have all the negative powers, that is n equal to minus p, starting from minus p, n again minus 1, and then 0 to infinity. These are the positive powers and these are the negative powers. There's a name which is given to this. This positive powers, this part is known as the analytic part, and the negative powers, okay, this is the series with the negative powers, this is known as the principal part. Okay, so we have two parts in the Laurent series. One is the analytic part, another one is the principal part. Okay, so now if Z0 is a pole of order p, then the principal part obviously will have a finite number of terms, because you see from minus p, it is only from minus p to minus 1. This is not an infinite series, it's a finite series. So this will happen if Z0 is a pole of order p. But if Z0 is a pole of order infinity, okay, in other words, if Z0 is a essential singularity, okay, if it's an essential singularity, then this will be it'll start from minus infinity, and as a result, okay, this principal part will have infinite number of terms. Okay, so now the convergence of the Laurent series. Okay, so if I have a Laurent series, okay, and the Laurent series has got infinite number of terms. Okay, so Laurent series, as we see, it's made up of two parts: the principal part, which contains the negative powers of z minus z0, and the analytic part, which contains the positive powers of z minus z0. Now these are two, so basically you're writing the Laurent series as a sum of two different series, one containing positive parts, one containing negative parts. So the entire Laurent series will converge if only both of these parts converge simultaneously. Okay, this is an important point. Okay, so both the parts should converge simultaneously, the principal part as well as the analytic part, both of them should converge simultaneously. Let's first look at the principal part. Okay, so this is the principal part. N goes from minus infinity to minus 1, a n z minus z0 to the power n. Okay, so this part will converge only if modulus z minus z0 to the power minus 1 is less than some constant, say k. Okay, how do we come up with this condition? I'll give you a hint. We can just use the ratio test. Okay, we can use the ratio test to come up with this condition. So I'll not go into the details of how we got this. I'll just leave it to you as an exercise. It's really simple. All you have to do is just use the ratio test and you'll arrive at this condition. Okay, so this part will converge only if modulus z minus z0 to the power minus 1 is less than some constant k. Okay, so z minus z0 is less than k, which means z minus z0 is greater than 1 by k, because we have inverted this, so this sign will get inverted, so it will be greater than 1 by k. This 1 by k, we'll just call it as r1. So z minus z0 is greater than r1. Now what does this look like? It looks like basically a circle, right? So we have z minus z0, this is the center of the circle, this is the radius of the circle. Only in this case greater than, that means you're talking about the region which lies outside the circle. So consider a circle of a radius r1 centered at z0. This region, this gray area, that shaded region that we have shown, take a z here, that z minus z0, that value will be greater than r1. So this region, okay, the exterior of some circle, and this circle, let's call it as C1. So that's the convergence of the principal part. Again, the analytic part. Okay, when will the analytic part converge? This part will converge only modulus of z minus z0 is less than some constant. Again, I'll leave it to you. This is very straightforward. Again, you can use the ratio test and you can come up with this. Okay, so z minus z0 is less than some constant. Okay, so if z minus z0 is less than some constant, okay, so this looks like again a circle. It looks like the interior of a circle. Okay, so here we have the principal part which will converge in the exterior of a circle, and the analytic part which will converge in the interior of a circle. Okay, so put these two together. If this radius, this r2, okay, this r2, if this is greater than r1, this is what will happen. R2 is the outer circle which is greater than r1. Remember, what is r1? R1 is the radius of that small circle, and this principal part is analytic in the outer region, and this one, okay, the principal part is analytic in the outer region, and the analytic part is converging in this region. So if this r2 happens to be greater than this r1, so you will get one inner radius and we'll get a outer radius. We'll get an inner radius and an outer radius. The principal part is convergent in the region which lies outside this smaller circle, and the analytic part is convergent in the region which lies inside this larger circle. Okay, so it means in that case the Laurent series will converge in this annular region, the region which lies between C1 and C2. It will converge within this region. Now remember, I said earlier that the Laurent series will converge only if both the parts converge simultaneously. Okay, so this is the only way this is possible. If R2 is greater than R1, then it is this region where this Laurent series is going to converge simultaneously. What about the other way around? What if R2 is less than R1? In that case, what will happen? R2 is less than R1. The analytic part is going to converge over here, the principal part is going to converge in this region. Within this white region, none of the parts will converge. So in this region, only the analytic part will converge. In this region, only the principal part will converge. Here, none of the parts will converge. So that means there is no region where both the parts are converging simultaneously. So that means this Laurent series will never converge in such a situation. It will only converge in this kind of a situation. So we can conversely say that if any function f of z is analytic in the annular region, this is known as an annular region between two circles, and C1 and C2, which is centered at z equal to z0, then such a function can be expressed as a Laurent series about z0, which converges in this particular region. Okay, so we can now use the Laurent series about z equal to z0 to actually classify the nature of this point z0. Okay. So if all the coefficients in the principal part are 0, that is an equal to 0 for n less than 0, that means for negative values of n, if an is equal to 0, that is if we get something like this, okay, so we have 0, 0, 0, 0 everywhere, right, divided by z minus z0, right, to the power 3, to the power 2 and so on. If the negative coefficients, okay, the negative coefficients, all of them are 0, then we say that f of z is analytic at z equal to z0. So it means in this case the principal part does not exist, only the analytic part is there. That means in this case the Laurent series becomes the Taylor series. Okay. Now if further to the above case, okay, in apart from this one, apart from all the negative coefficients being 0, let us say that the first k coefficients in the analytic part are also 0. Okay, that is am equal to 0 for 0 less than equal to m less than k. So for instance this, so we have all the negative coefficients, they are all are zeros. Okay, then we have a0 is 0, a1 is 0 and so on. A k minus 1, that is also 0. Okay, that means ak is the first non-zero coefficient. Okay, so if in addition to this case, if we also have this case holding good, then we say that this f of z has got a 0 of order k at z equal to z0. So z equal to z0, in that case it is known as a 0, and it's a 0 of order k. Next, if there are finite number of terms in the principal part, okay, that is there exists some integer p such that a minus p is not equal to 0, but a minus p minus k is equal to 0 for all integers k greater than 0. In other words, if we have a pole of order p, okay, so then in that case the principal part will have finite number of terms. So if that happens, okay, so we have starting the first non-zero term will be a minus p term, and then all the other terms, that a minus p minus 1 minus p minus a minus p minus 2, all of these terms, all of them will be zeros. Okay, so starting a minus p and so on all the way in the analytic part. Then in that case, of course, just by looking, if you see the Laurent series like this, then you can easily guess what will happen. We can say that the function f of z, it has got a pole of order p at z equal to z0. And if there are infinite number of terms in the principal part, then of course this is going to be f of z will have an essential singularity at z equal to z0. Okay, so now let's take a look at an example. The example is f of z equal to e to the power z by z minus 1 to the power 3. As we have to expand this function as a Laurent series about an appropriate point. We have to identify the type of singularity, and we have to give the region of convergence for this series. Okay, so now we can see here directly that this function is non-analytic at z equal to 1. So it means z0 we choose it as 1. Okay, so this will be your z0. So now what we'll do is we'll introduce some other variable t, that t is equal to z minus 1. Okay, so hence if t is equal to z minus 1, that means z is equal to 1 plus t. So you just substitute it back here. So e to the power twice z, so 2 into z. So z we can write it as 1 plus t, so 2 into 1 plus t is 2 plus twice t, and z minus 1 we write it as t, so it becomes t cube. So we have e square by t cube into e to the power twice t. Now this is really straightforward, because e to the power twice t we already know it's a Maclaurin series, right, for about t equal to 0. Okay, about t not equal to 0, we can just expand this as a Maclaurin series, and this is what it's going to give us 1 plus twice t whole square by 2 factorial and so on, and then we have e square by t cube. Okay, so now all you have to do is just multiply this 1 by t cube term by term. Okay, so e square 1 by t, 2 by, there's a t here, so we'll get a t square, there is a t square here, and t cube in the denominator will get a 1 by t. T cube and t cube will get 4 by 3. Then we have t to the power 4 by t cube will get a t here, t square, and so on. So this will be the expansion. Now we just need to substitute back this t equal to z minus 1, just substitute it back here. So this original function is equal to e square times 1 by t cube, which is z minus 1 cube, 2 e square by z minus 1 square, 2 e square by z minus 1, and so on. So this is going to be the Laurent series expansion. Okay, so here what I have done is I have used a node, because the moment I see e to the power twice z, the moment I see this, I know that okay, I can now, there's an exponential term in the numerator, so I could just maybe use the Laurent series, Maclaurin series expansion, do some substitution here and there, and we get directly the Laurent series expansion. Okay, so now by looking at this one, okay, so we have to identify the type of singularity. So which is the singularity? The singularity is z equal to 1. What type of singularity it is? Look at the Laurent series. The Laurent series, the principal part has got finite number of terms. Only 3 terms are there in the principal part. Okay, so which one is the first term? The first one is a minus 3. Okay, a minus 3 is equal to e square. So a minus 3 is the first one. So a minus 3, that means this must be the order of the pole. So z not equal to 1 is a pole of order 3, which makes sense because we directly by looking at the function itself also we can guess this, but the Laurent series also it confirms the same. And the series converges for all points except at z equal to 1. Okay, it does not converge at z equal to 1 because that's where it's going to blow up. Otherwise it will converge at all points. So we can just say z minus modulus z minus 1 is greater than 0. So that's the region of convergence. Okay, next example, we have to expand this particular function 1 by z plus 1 into z plus 3 as a Laurent series in the region 1 less than modulus z less than 3. Now you can see here this is basically an annular region, right? 1 less than modulus z. So this is so we will have to this is basically it's a circle. Okay, z minus z naught, modulus z minus z naught is 0, so it's a circle whose center is at 0. Okay, and there are 2 radii, one is the inner radius and one is the outer radius. The inner radius is 1, outer radius is 3. So we have 2 circles, one is the inner radius and one is the outer radius. Center is 0, one circle of radius 1, another circle of radius 3. Okay, that's the annular region that we are talking about here. Okay, so this is a region of interest. So we have centered at 0, so we have one circle and we have another circle. Okay, so one circle of radius 1, another circle of radius 3. Okay, all right, so now what we have here is z is greater than 1, right? Modulus of z is greater than 1. That means this dotted line that we see, it will not be included because this dotted line corresponds to this dotted circle, it corresponds to modulus of z equal to 1. Because it's greater than 1, it will not, this will not be included. Again, modulus of z is less than 3. This larger dotted circle corresponds to modulus of z equal to 3. This is not included, so it will be slightly inside. Okay, so now what we can do is we can resolve this function into partial fractions. I have already shown you in class how to find out the partial fractions. So basically a function 1 by z plus 1 into z plus 3 is equal to a by z plus 1 plus b by z plus 3. So we resolve this into partial fractions, and we can see that this will be equal to half into 1 by z plus 1 minus half into 1 by z plus 3. You can just verify this on your own. So this will be the partial fractions. Okay, so now here we are going to use this result. The result is 1 by, if modulus of q is less than 1, 1 by 1 plus q is equal to 1 minus q plus q square minus q cube plus and minus and so on. Okay, so this actually is from your result that we are using from geometric series. Okay, is just using this result from the geometric series, infinite convergent geometric series. We are using this particular result, so we can use this following result to resolve these two. Okay, so now why did we resolve this function into partial fractions? The reason is this. You see the poles here. One pole is at -1, another pole is at -3, and here the region that we are talking about, it lies between 1 and 3. The radius lies between 1 and 3. So this gives us the opportunity that if we can resolve this into partial fractions like this, we could, if I can find out the expansion of this partial fraction and the expansion of this partial fraction, such that one of them gives us the principal series, the principal part. Another part gives us the analytic part. Then that will give us the entire Laurent series, because if this suppose the principal part is converging in this region, and the analytic part is converging in this region, then we know that in that common region the sum of these two series will always be convergent. Okay, so that's basically what we are going to attempt to do here. So using the two region constraints and expanding the terms in 1 and 2, we can separate the principal and analytic part of the required Laurent series. Okay, so first what we'll do is we'll take this part, that is 1 less than modulus z is same as modulus z greater than 1. So from modulus z greater than 1, we have 1 by modulus of 1 by z. If I take just invert this, modulus of 1 by z, this greater than will become less than, so modulus of 1 by z is less than 1. Okay, so we'll take the first term in equation number 1. This is equation number 1, the first term, half into 1 by z plus 1. Okay, we'll take the first term, half into 1 by z plus 1. We'll take the first term here, and then what is you take the z common outside. Okay, you take the z common outside, so we have 1 by 1 plus z. Okay, so now what we see here is 1 by z. If you compare it with this equation 1 by 1 plus q, and if modulus of this q is less than 1, then this is the expansion. So you can see here this is satisfied, because 1 by 1 plus q, this is your q, 1 by z is q, and modulus of q is less than 1. So the expansion which is given in equation number 2, it is applicable to this quantity. Okay, so as a result 1 by 2z. So what is the expansion? The expansion is basically 1 minus q plus q square minus q cube and so on. Okay, so 1 minus q is 1 by z plus q square 1 by z square minus 1 by z cube and so on. So this is the expansion. The next step is you just multiply this throughout. 1 by 2z, you multiply this throughout, and you get 1 by 2z minus 1 by 2z square and so on. And you can see here this expansion, okay, this expansion, it has got only negative powers of z. Okay, so if it's got negative powers of z, then this seems to be like the principal part. Okay, so for the other part, that is modulus of z less than 3. Modulus of z less than 3, so if I divide this throughout by 3, we get modulus of z by 3 is less than 1. Now consider the second term, 1 by 2 into z plus 3. So here if I take 3 common outside, so 3 you take it common outside, you will get 1 by 6. 1 divided by, this will give, there will be a 1 here, and there will be a z by 3. Again you see here 1 divided by 1 plus q, this is q, z by 3 is q, and modulus of q is less than 1. So condition is satisfied. That means this can be expanded as given in equation number 2, and that's what we do here. 1 by 6, 1 minus, this is q plus q square minus q cube and so on. Okay, so just multiply this 1 by 6 everywhere, so this is what you get. So 1 by 2 z plus 1 is this, and 1 by 2 z plus 3 is basically this. So all you have to do is the required Laurent series expansion, which is valid for both, okay, this region, that is modulus z greater than 1 and modulus z less than 3, that is 1 less than modulus z less than 3, will be the difference between these two, because as per the partial fractions, this is the first series and this is second series. You take the difference between these two. This is convergent in the region which is modulus z greater than 1. This is convergent in the region modulus z less than 3. So it means in that annular region both of them will be convergent. So the difference between these two, that will be the Laurent series. So you just take the difference between them. This is the Laurent series expansion. And as you can see here, there are infinite number of negative powers. So it means this must be this z equal to 0. Okay, here that must be a essential singularity. Okay, so these are some problems which I'll leave it to you as an assignment. Okay, so we'll stop here. These are some reference books that you can follow. This is the book that I was talking about earlier. This is Murray Spiegel's excellent book, Theory and Problems of Complex Variables. It's given in a very, things are written in a very succinct manner, and it has got lots of problems to solve. So you can go through this book if you want. So this brings us to the end of this lecture. As before, I have uploaded this video on your Google Classroom, and I have also uploaded the slides there so that you can refer to them later on. So we will stop here. In the next class we will discuss the last topic, final topic in this module, which is the residue theorem and its applications. So I hope you'll take care of yourself and your families. Goodbye for now.